Welcome to After Hours Engineering, Episode 2, Verilator. In this episode, we'll take a closer look at Verilator and how we'll use it to simulate range of RISC. We'll take a look at the manual, some header files, some macros, then a VCD, then what I call property shadowing, a test bench or two, and then finally linting. So without further ado, let's launch right into looking at Verilator. So here we are at the Verilator website. It's the first place to come to when you want to get the latest documents out there. You just come right up here to Verilator, go to documentation, and you can pull down the PDF, the latest one, or you can look at the latest web one. And that's where we're at. The two main features that we'll look at in this document is the language extensions and files. We'll take a look at the files first. When you run Verilator, it's going to parse your system Verilog or Verilog and place it in an output folder. This is all the files that it generates, and there are several key files that we'll look at in a minute. So let's take a look at the language extensions. This is the main section. It's the most of your Verilog. And we're going to be looking at the Verilator lint off and lint on features, but Verilator has a considerable number of extensions that you can use. Blocking, clocks, interfaces, configurations, a whole number of things, working with clocks and coverage. But we're going to focus on only two of those, and the first one is the Verilator linting features, where we turn linting on or off. We won't be using any of the stack features, but you can certainly pop linting flags on and off the stack. The other extensions we'll use extensively is the public and public module features. That's all of these right here. Here's public module, and we will be using the public variable, type enum, and parameter. This is what we'll use out of the language extensions. The other section that we'll look at is the file section. This is the area where when you run the build for Verilator, it will generate a whole sequence of files. They're important because they'll tell us what we can include in our test bench. We're going to focus on the module header. We'll look at the root. We'll also look at any symbols, and finally any of the Verilog modules that we export as public. These four key header files are what we'll use to build our test benches with. Verilator comes with quite a bit of macros. One of the most important, if you're going to do console type simulation, is the printf statement. I recommend that you use their macros to do that kind of work because they're set up for a multi-threaded environment, and Verilator is definitely a multi-threaded simulator. So if you are going to use any kind of printing to the console, I strongly suggest you use their macros. The most important is the VL-printf macro. Next, we'll talk about an effect I call property shadowing, and we're going to use the memory module test bench as an example of that. So over here to the rightmost tab, we have the memory module test bench. And the phenomenon that I'm talking about here has to do with an inner versus an outer module. To the middle pane here, we have the outer module, and it has all of the parameters that are on the memory module itself. So let's take a look at the actual HDL memory module. And here is our inputs and our outputs. We're going to look at pretty much all of these input signals here. So this is our module. Now we come to the Verilator module that exposes those parameters on that module, and here they are. This is considered the outer module in Verilog. This one is the inner module in Verilog, and the leftmost pane is that module, and you'll see yet again we have the parameters on the module exposed. So now that we can see that we have the HDL module, the Verilog wrapped up version of that, the actual Verilator module, and the Verilator root here in the middle, we'll now come over to the test bench and take a look at what's going to happen. So we have our core memory module itself, the Verilator module, the root, which has various modules within it, and I've gone ahead and gone to the root and asked for the memory module. Here it is. We can dump the memory out. We can look at any particular memory address. That's all fine. But what starts to break down is when we try to use that inner module to change various signals. In this case, I'm changing the right one. And when we run the simulator, we'll notice that everything seems to be working fine. We've got a 1, then a 0, then a 1, and it'll show up in the console. Things start to break down when we use all of the signals on the module, including, like, say, the address one. If we run this module, this test bench, we'll see that things aren't working quite right. For instance, when we get down here to time step 50 and we take a look at the memory, we'll see that it isn't correct. So if I come down here to the memory module and I look at it, we have a 1100B. The problem is that's what the memory was when we started the simulation, and we expect after the simulation runs that that same memory location has A0, A0. So if we scroll down to the bottom of the simulation here, the memory location still has the OB in it, and that's not right. It means we're changing signals that Verilator itself isn't seeing. We're changing the inner one when we need to change the outer one. So we need to come by and change all of these to top, and then when we rerun the simulator. But now before I do that, let's run the simulation and take a look at the output. This is the output, and you'll see that any of the input signals here are not changing signals. None of the addresses are. So GTK Wave is not seeing any activity on those signals. So we'll come back over here. We'll change all of the accessing from the inner to the outer one, the root. We're going to rerun the simulation here. It can go. And as you can see, we have all the signals are back on and in GTK Wave. We can see the read, the write, and the address lines changing. And this is what we expect. In addition, if we come down here to the output, we'll see that memory location 5 has been updated with the correct values, A0, A0. So going forward, be careful with what module you're actually changing signals on. More often than not, depending on the test bench that you're doing, you're going to change the signals at the top level and not at the inner module level. But there are exceptions. If your parameters or the variables that you're trying to change are not part of the module parameters, you can change those, and that's the case here with the memory bank, and that's fine. What the problem becomes is when you start changing module parameters at the wrong level, and you'll notice that things aren't working. But that's it. That's the general rule. A lot of our simulations are going to be based off of viewing signals inside of GTK Wave. In order to do that with Verilator, we need to do a few configurations and setups. It begins with our module.h file that we've taken off of Zip CPU, and we've made a few enhancements to it. One of them is we've added in the VCD initialization sequence. In order to do that, if we come over here to our module.h file, we add a few lines of code in here that will start up and initialize the VCD features, including telling it what the output file name should be for the VCD. Also, when we want to shut down ours, we need to shut the core down and shut the trace down as well. That's all there really is to doing GTK Wave inside of that. In the test bench itself, we need to add in the VCD file. This will have all of the features and mechanisms that we're using over here inside of the module. And that's it. Once you do that, you'll start calling the evaluation, and then you'll call any kind of dump features that will output everything to the VCD file, and at the end you'll close it and shut everything down. And that's what happens in our shutdown method that we do at the bottom of each one of our test benches. That's it. That's how you would use VCD with Verilator. Now let's take a look at two different styles of test benches. One is based off a unit test, and the other one is based off of a clock generation. We'll start with the unit test. And for that one, I have it built into the instruction register test bench, which is what we're looking at right here. In here we have just the reset sequence and the fetch sequence, which both test the instruction register. We'll take a look at the reset sequence and see how it's structured like a unit test. So we come over here to the reset sequence on the right, you can see that we have a loop going on. This is a clock generator, but nothing is going on other than running out the clock so that we can then finish looking at the reset sequence. We can see that there is a clock running up here in a loop, so this is a generator, but we don't do any assertions in it. We wait until after the loop is complete and then we begin making assertions against the state of the machine. In this case, we know that once the reset signal goes high, we should be in vector state 0. That's according to our diagram. We know that the next state should be ready for vector 1, and the reset state should be set to a 1, and the ready should be set to 1. This is a unit test style. You don't need GTK wave to see these things. And when it fails, it'll come over here, check for the assertion failure, and then abort, which shuts down all of the other modules. The same can be said for the fetch sequence. If we come over here, again we have a while loop, but in this particular one we are running a clock, but we're making assertions while the clock is running. And as soon as we find them, we've transitioned to this one and we print it out. At the end, I could have done an assertion to check to see if the fetch state was reached. Now this is an example of a unit test approach. Now let's take a look at a clock generator approach, and for that one we'll look at the main RISC processor. You can see that we have the same reset sequence going on, but we now have this loop style thing that's going on, and then we eventually just run a few extra clock cycles to spread it out in GTK wave. So for this one we'll need to take a look at the loop cycle, and you can see that we're doing nothing more than running a clock out. Everything that we're going to do is going to play out in GTK wave. We'll inspect the output of GTK wave instead of doing assertions. So this is two different styles of working your test benches, and it depends on what you're doing as to which style you will use, and you can actually blend them together. Now we finally look at the linting part, and early on when I was building the RISC-V processor, modules weren't using all of the signals, especially the test benches, and so they were all stopping to run, telling me that I had unused bits. So in order to control that, you can add in the lint off and then turn it back on with the lint on. Now I can remove these two and it'll continue to work right now because with the processor in its complete state there's no longer any unused bits. And the same goes for the MMU. I originally was turning off these because some of the bytes out of the function 3 and byte address weren't being used. I can technically take these back out, but I'll leave these in for people to view and see, but they're not actually used. And that's how you control your linting. And there are many lint flags that you can use and take control of it depending on the state of your machine when you want to turn them off or push them onto a stack. But this again is an example of turning on and off linting during development. As I've said, the RISC processor is built. I don't really need these anymore. And that's it. There you have it, a moderate overview of Verilator. There's so much more to what Verilator can do, but I've chosen to limit the features so that we can maintain focus on the RISC-V processor. In the next episode, we'll begin looking at the RISC-V ISA in order to put us into a good starter position to help us feel confident of what our end goal is, which is a fully functional RISC-V software processor. So until next time,